Okay, this is the video lesson for average and instantaneous velocity. This is derivatives day 2, and I believe that that is written up at the top of your notes. Derivatives day 4. Okay, so let s of t be the position function. This is nothing new. You've seen this before. This shows how high the ball is or where it is, okay? Over a period of time, delta t, we've seen this delta means change. An object will change position by, and what we see is we have this change. We have the position after time t, so we'll say there's a time, and we're going to change that time by a small increment, and we're going to subtract that from whatever original time we were talking about, the position at the original time. This right here is called delta S. This is the change in position, okay? So let me show you what this looks like on a picture. And this is going to look similar to what we did in derivatives day 1. So let's say we have a time t, and then a little bit later than that we have the t plus the change in time t, delta t. And let's say we have a point here, and let's say this thing is falling. And so, this doesn't have to be a straight line. It's probably going to be a curve. It could go up and come back down, or it could be falling this way. Either way, whatever is happening, when we're looking at average velocity, we are actually going to be finding this dotted line that I'm going to draw here in blue. That right there is the average velocity. Okay, it's the slope of the secant line. Okay, so when we see average velocity, all right, we need to think secant. Okay, so let's think about how we find velocity or rate normally. We have d equals rt. We know this formula, and if we solve it for r, we get d over t. Okay, so r here is our rate. This is standing for our velocity. So let's think about, d is distance, t is time. So when we're trying to find this velocity, it is going to be the change in position over the change in time. And you may be thinking, well, yeah, that's obvious. But I'm kind of building it up, relating it back to what we've done with derivatives, and I'll get to the derivative part in a minute. Okay, now change in s. We already saw that this is s of t plus delta t minus s of t all over delta t. Okay, this right here is what we call average velocity. This is the secant line. All right, so let's see what happens here. We'll get to the instantaneous part in a minute. So let's say a billiard ball is dropped from 100, and this should say 100 feet. All right, so 100 feet. Let s equals negative 16 t squared plus 100 represent the position of the ball at time t second. Find the average velocity over the specified time. So you need an interval to find average velocity, and we're going to be dealing with simply 2 numbers, not many, many numbers, okay? So we need to find s of 2 minus s of 1 over 2 minus 1. Now this should remind you of 2 different things. It should remind you of average rate of change, which we saw this semester. It should also just remind you of the simple slope formula. Okay, so you can use your calculator on here. S of 2 gives you 36 feet, and S of 1 is 84. And then we're going to divide that, in this case, by 1, and that's going to give us negative 48, and we're going to put it in feet per second. I know in science you're used to meters, so you have to pay attention which units you're in. If you see a 16 here, though, you're going to be in feet. That's always going to happen. Alright, so the only thing that's changing here is I'm minimizing the change in t. Up here, change in t was 1, now change in t is only 0.5. But we're going to do this the same way. S of 1.5 minus S of 1 all over 1.5 minus 1. And here we're going to get 64 for the S of 1.5, again minus 84, and 1.5 minus 1 is 0.5. And so you can calculate that, and we get negative 40 feet per second. And this should make sense that the speed here is less because it's a smaller increment. We're getting closer to the beginning, and we know the speed, it's going to speed up as time goes on. So this number should be decreasing. All right, and so you probably can figure out what we're going to do for the last one. Same thing, we just have different numbers, s of 1.1 minus s of 1 all over 1.1 minus 1, and that is going to give us 80.64 minus 84. If you have questions about how I'm getting these numbers, please ask me tomorrow in class, over 0.1, and that gives us negative 33.6 feet per second. And again, that number decreased. And as I lower this increment, as I get the second number becomes closer and closer to 0.1, I'm getting closer and closer to the instantaneous velocity. I'm just going to abbreviate here because you're going to see it written out right below this. So the instantaneous velocity at what time? At t equals 1. This increment's getting smaller and smaller. The secant line is going to become more like a tangent line, and that's where we're going to bring in derivative. So one thing to note here, I think everybody in physics knows this, but if the velocity is negative, the object is moving down. You could say in an opposite direction. In this case, though, the direction would be down. Instantaneous velocity, average velocity over a small interval, and below this instantaneous, I want you to write tangent line. And anytime you think of tangent, you need to think of derivative. So the velocity is the derivative of the position. And for speed, we're just going to take absolute value because speed does not have a direction, only velocity has a direction. So in general, our position is going to be 1/2 times the gravity times time squared plus the initial velocity times time plus the initial position. Generally, though, this is given to you, but you should be able to come up with this equation on your own. Here are the two numbers for gravity. This is why you see negative 16 a lot, because we're doing half of negative 32, and you see negative 4.9 when you're in meters, because that's half of gravity in meters per second. And that really should say squared there. Okay, so let's move on to another example. So on 2, it says the position of a diver t seconds after she leaves the diving board is given by this. So we can see here that we are in feet per second. The initial velocity is 16. The initial position is 32 feet high. When does the diver hit the water? This is an Algebra 1 question. This is not anything overcomplicated, so don't overcomplicate it. When does the diver hit the water? That happens when her position, or his, does it say she? It does say she. When s of t equals 0. Okay, so you're going to find the 0 in your calculator. You can do this by graphing and finding out when does the diver hit the ground. You could do where you have y1 up here and you have y2 equals 0, and you find the 0 that way. You can set the equation equal to 0, negative 16t squared plus 16t plus 32. Set that equal to 0 and either factor, or maybe factoring doesn't work, do quadratic regression. You end up getting t equals 2 seconds. I'm not going to spend time on this because I've shown this in other lessons. And like I said, this is an Algebra 1 concept. You're still more than welcome to ask me more questions about it later. Okay, what is her velocity at time t? Now, when you see just velocity and that word average is not in front of it, they mean instantaneous velocity. And when you see instantaneous velocity, you need to find the derivative of your position function. So this is where we're going to use power rule. 2 times negative 16, that's negative 32. The power on t, we subtract 1. Okay, now moving over here, the derivative of 16t is just plus 16, and the derivative of 32 is 0. So this is a really nice use of power rule on an actual application problem. This is the velocity function. The derivative of the position is the velocity. We saw that. So now it says, well, what is her velocity on impact? Well, we saw up here that it took 2 seconds. So really what we're finding is the velocity of 2, or you could call it s prime of 2. We're going to take our derivative function and we're plugging 2 in. So we're doing negative 32 times 2 plus 16. And again, you're going to use your calculator for this. And that is negative 48 feet per second. And that should make sense that her velocity is negative. She's moving down. It says, what is her speed on impact? Well, her speed is just going to be the absolute value. So that's going to be 48 feet per second. Some people get confused with the S up here with speed. This S stands for position. With speed, we just write the word to be super clear. All right, D, when does her velocity equal 0? So again, we're looking at her velocity function, negative 32t plus 16, and we're setting it equal to 0. And since it's a linear function, you should be able to do this quite easily. Solve for t, and you get 0.5 seconds. You are more than welcome to use your calculator as much as you want on any of this section. Okay. E says, how high is she when her velocity equals 0? Well, we know her velocity equals 0. That happens at t equals 0.5 seconds. When they're asking, though, how high, they're not asking about her velocity, okay? They're asking about her position. So you need to go back to the original function and find s of 0.5. And so this is going to be negative 16 times 0.5 squared plus 16 times 0.5 plus 32. Or you could have typed that in your calculator and then gone to the table. You have a lot of options here on how you actually solve it, but this is what you're doing. You're plugging in 0.5 into the position function and you're getting 36 feet. All right, now let's look at the next one. What is her average velocity over this time interval? Remember, average velocity is not instantaneous. We're not looking at the derivative. We're looking at the original function. We're looking at the position function. We're finding s of 1.5 minus s of 1 over, this is what we did on the first page, 1.5 minus 1. Okay, so we're kind of going back to a less accurate answer because we're going over an interval. And so this is going to be, when you put the numbers in, you get 20 minus 32 over 0.5, and you get negative 24 feet per second. That is her average velocity over that interval. And the last question says, well, at what time is the average velocity equal to the instantaneous? Okay, well, remember that our instantaneous velocity is represented by our expression negative 32t plus 16. This is the instantaneous velocity. We want to know, where is that equal to her average velocity? Well, we just found her average velocity. So let's set it equal to negative 24. This is not about memorizing what to do on each step. It's about just thinking logically about what you have and knowing what all the terms mean. All right, the word velocity is thrown around a lot in here. You have to understand the difference between average and instantaneous. Here, now we're just going to solve for t, and you are going to get t equals 1.25 seconds. Okay, so this is just one application of when you would need to do derivatives. There are many. Bring your questions to class.